Hello, my name is Timothy Gallagher, and this is my Lab 5 Magnetic Braking with Faraday. In this lab, we will collect observational data of a magnet falling through a conductive tube of aluminum foil, model the magnet-tube interaction computationally, and compare computational predictions with the observed data. We will be using several concepts and equations in this lab. First, we will be investigating Faraday's law, which is an electromagnetic law predicting how a magnetic field will interact with an electric circuit to produce an electromotive force, which is the fundamental operating principle behind transformers, inductors, and many types of electric motors. Additionally, a magnetic dipole is similar to an electric dipole. It is the limit of a closed loop of electric current, or a pair of poles as the size of the source is reduced to zero, while keeping the magnetic moment constant. Lenz's law states that the direction of the electric current induced in a conductor by changing a magnetic field is such that the magnetic field created by the induced current opposes changes in the initial magnetic field. It specifies direction, but not magnitude, of the induced current. Magnetic flux through a surface is the surface integral of the normal component of the magnetic field B over that surface. In addition, we can see the equations for the magnetic field of a dipole and Faraday's law to the right. Moving on to the experiment, after recording the properties and dropping the bar magnet through a aluminum foil tube 5 times, we can see the results in the table to the right. The average time it took for the bar magnet to leave the tube was 1.622 seconds during the 5 trials. We can note that the magnet fell slower than the free fall due to interference from Faraday's law. Moving on to the computational model, after setting the measurements of magnetic constant mu from Lab 3, we obtained the velocity versus time graph shown to the right. The graph shows an initial rapid increase in velocity, with the velocity leveling off over time due to the aforementioned interference as predicted by Faraday's law and the current in the tube. The computed time for the magnet to leave the tube in the computational model is 1.327 seconds, as shown to the bottom right. My observed average for the magnet to leave the tube was 1.622 seconds over the 5 trials. This is a close estimation, but several factors, such as friction between the tube and magnet, initial forces inadvertently added, and time and measurement errors during the experiment could be causal factors in the 0.3 second difference between calculated and observed times in the experiment. Moving on to the discussion of the first question. What if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? The braking force would gradually reach a point that would greatly slow the magnet. The closer to zero, the slower the magnet would fall in this experiment. Finally, what if holes or slots were cut into the tube? How would this affect the ring currents in my model? The normal flow would decrease as the amount of current that could flow through the tube would be lessened. The magnet would therefore be able to fall faster through the tube with less resistance, and my predicted time would be lower than the 1.63 seconds that I observed in this experiment. Thank you. This is Lab 5, Physics 2.